最初，克莱奇奥化学抢救术，阿隆其他科目加盟南京大学，教导好学。此外，近百名诺贝尔奖得主和世界人文艺术大师也都走上了南法的讲坛，分享自己的学识和人生经验。南京大学每年都会迎来各国政要、世界著名企业家等社会名流到访，当中。
This one? Okay, start. So let me review a bit some part from yesterday. We talked yesterday about fairness. And we discussed this issue that the usually simple intelligent model has some deficiency in that it just says, well, start with some initial state, pick up and enable transition, and then another one, and another one, another one, and kind of it allows you some executions where, say, one process can execute something indefinitely or infinitely often, but would never get the chance to do it. So sometimes you want to remove, exclude these sequences, and this is called fairness. Fairness means that I exclude some of the sequences, and so sometimes I want to do model checking with respect to some fairness assumption, and we saw this example of Decker's algorithm that without a fairness assumption it would not work, simply because a process may want to give up and allow the other process to get to the critical section because it's not its turn, but it just takes the cycle, and doing nothing, doing some loop. Just ask, is that my turn now? Is that my turn now? It's not. Just let the other guy take its turn and continue. Now, it's not trying to get the critical section. It just waits for its turn again, allowing the other one to enter, but it steals all the cycles. That's not a fair execution. We looked at different kinds of fairness conditions. It's just a review, right? Because I think that part was a bit difficult. Different kind of fairness conditions, weak transition fairness, weak process fairness. Whether we are fair with respect to every transition or we're fair with respect to the process, meaning that if one of the transitions of the process is enabled and one of the transitions is executed. Strong as opposed to weak fairness means that if something is enabled infinitely often and not continuously, then still it is guaranteed to execute. One thing, well, we did some example, and one thing I kind of skipped maybe too quickly. This thing is, again, a very complicated specification of fairness within LTL, which theoretically works, but it's really not practical because the formula would be as big and even bigger than the program that you want to check itself. We talked about the fact that alternatively you kind of modify a little the algorithm, the way you check for strongly connected components. And this thing I kind of skipped yesterday. This says, it kind of shows the relationship between the different fairness assumptions. So in fact, if I have like a node here, and I have a node there, and there's an arrow, it means that if an execution is fair with respect to strong transition, it's strong transition fair execution, then it's also strong process fair execution. Okay, so that fairness is stronger in the sense that it allows less executions. Okay, there's less executions that are fair like that, and there's more like that. There's even more executions that are fair like that, and in fact, these all are included by all the executions. All the executions include all these sets. And what's the point of that? As I said yesterday at the end, you may not know what is the actual fairness assumption that you should take, right? You could kind of guess it, or you could try to measure it, or you can use your experience. But the fairness sometimes depends on some kind of physical constraints of the system. So if you don't know, the best thing to do is work with the weakest fairness assumption. So weakest means the one which excludes the least, that allows the most executions. I mean, the best is to do without fairness. Try to do the verification, okay? And say, if you did the verification here and you find no error, that means what? It means that since you found no error with the larger set of execution, with the weaker fairness condition, it means that also under stronger fairness condition, this is also true, because this is a smaller subset of executions. All of these are good. a smaller subset of that is also good, and of course this is also good, right? So try to use the weakest or the fairness condition that exclude the least number of executions, okay? If you don't know, if you're not sure, okay, and then if you couldn't, then use a stronger fairness, okay, but then maybe you excluded too much, but that's life. Also, as I said yesterday, the weak fairness conditions, they are easy to check. The algorithm is simpler, so it's a simple modification of the algorithm that looks at reachable, strongly connected components, just that it checks that the component is fair, has similar property to the fairness condition. So if I want a weak transition fairness, that I want to find a strongly connected component that every transition that is enabled in that component is also executed. Okay? Or if I want a weak process fairness, that every process that is enabled in that component is also executed. One of its transitions is executed. So the change to the algorithm is very small. These require pretty difficult, very complex algorithm. I'm not sure there is any tool that is kind of useful nowadays that implements that, unfortunately. To be honest, I do not believe in strong transition fairness. So if someone gives you some program and it works because you need the strong transition fairness, I would say his algorithm is not so good, right? It's the really strong assumption that if something is enabled infinitely often, then it would be taken, right? It's kind of statistical, okay? I'm not always enabled, but you know, I'm enabled again and again, indefinitely often. At some point, it cannot miss me. My feeling is that, you know, this is not right, because maybe I'm enabled every 2 milliseconds, and it's going to check also every 2 milliseconds, but at the time that I'm not enabled. So it's kind of philosophical, right? So my claim is that these strong fairness conditions, not only they are difficult to check, and these are actually a very small change. These are kind of, I would say, I wouldn't trust a program that works that require to have strong fair conditions, right? It requires to exclude too many executions because I'm not sure. Even statistically, yes, if something happened indefinitely often, then statistically at some point it would happen. But if it's synchronized, right? If the scheduler is synchronized, it can miss it infinitely often, right? So I would say we don't worry about the fact that we have these strong process fairness. These are just examples for fairness conditions. These are the most commonly used. There are others. Okay, so now we finished the thing about fairness, and we have to go. We skip quite a lot. Let's see. I'll do that because the next section. The next part is now we're going to look at. At a completely different thing. Okay, so we saw up until now that we do model checking and modeling just by using algorithms on graphs, right? The state graph of the program that represents how the program behaves, right? Represents directly the reachable states and the transitions, and it represents the path. If you apply the algorithm I talked about, it would be very hard to do that for programs that have a lot of states. I would say if the program has, say, a few million states, this is doable. And if it has more than a few million states, then the method I show is kind of not practical. Now, something that I wouldn't have time to speak about, but it would be in the slides that you will get. There's something which is called abstraction, which means that I map the program into a smaller program, kind of preserve some of the properties. Again, like in all the cases I talk here, mapping the program to a smaller program that represents whatever I want, again, it's the responsibility of the person who's doing the modeling, right? So it's a point where I can make errors, right? So it's one of these points where if I don't map it correctly, then it's wrong. A lot of times, the person who's doing this mapping, this abstraction, is an expert. A lot of times, the guy who wrote the tool, right? And the mapping should preserve all kinds of properties, like simulation relation, okay, homomorphism and stuff like that. I'm not going to talk about it, I don't have time, okay? And also, this is one of the things where I put the man in the middle of the process, right? I'm relying that someone would come and would do the modeling in a more manual way, right? Because I'm not just translating, but I'm kind of abstracting and reducing the complexity, not automatically much more chance for errors, okay? But a lot of times there's nothing you could do. I mean, the guy who wrote spin, he went to NASA and they wanted him to verify part of this spaceship Cassini, okay? So how did he do that? He didn't take the, I don't know, millions of code of C. What he did is he wrote a model himself, right? He studied it and he wrote a model. He found an error, okay? But this is because he's such an expert in doing that, right? If I would have done that, I probably would not model it correctly because I don't know how to program. Okay, so now what we're going to do is we're going to learn an alternative way of doing model checking. And that alternative way actually works better for a different kind of logic. So that's an opportunity of seeing a different kind of logic. The two logics, temporal logics that we're going to see are kind of complementary. So they can express properties that they're not disjoint, but some properties can be expressed in one logic and some properties in another logic. There are different advantages and disadvantages. And in fact, the people that invented model checking, they started with this logic. So instead of the logic LTL, linear time temporal logic, they started the logic which is called CTL, or computation tree logic. Okay? So the two groups in France and in the US that invented model checking, they started with this logic called CTL. It is a bit similar, but the idea now is that before, in LTL, the time was linear, right? So it started and then it went kind of with the time, there was only one choice. And here, we look at branching time. Okay? So branching time means that if I am in a state, then I'll have branches according to the possibilities. And the possibilities could be because I have non-deterministic choice. And usually they are because I have concurrency, right? So if you looked at the model I have for the mutual exclusion, you know at the first lecture, remember that model? So that was a branching model, right? From a state, you can have several choices, okay? And if you unfold that model, so if you take that model and you unfold it in the sense that you start with an initial state and then you draw its successors and then their successors and their successors, you don't close loops, you just unfold it. So you get an infinite tree, right? And that will be the unfolding of that graph into a model. So instead of looking just at one sequence or at many sequences corresponding to the sequences of the execution, I look at an unfolding of the model. This is basically just going to one state and then its successors and their successor, etc. with repetition. I mean, it could be that this successor is the same as that or is the same as that, I don't care. Okay, no loops. It's just an unfolding, and that gives me a tree. So one of the advantages of doing that is that with this logic, you can say things about choices, right? Before that, you say in every execution something happened, okay? But you have to say something about all the executions, right? So if you wanted to say that in some executions you reach A, and in some executions you reach B, you couldn't say that. You could say, in all the executions I reach A or B, but it didn't actually mean that you could reach A and you can reach B. It could be that all of them were A or all of them were B, okay? So it's a different expressive power. Here we have the advantage of being able to talk about choices, there we have different advantage we're going to talk about. Okay, so it's a bit of a different logic. The nice thing about this logic is that the complexity of model checking here is better. And before that, the complexity was actually exponential in the size of the property. And why? Because you can check that the algorithm, the complicated algorithm I showed you, can result in an automaton, a Douchy automaton, which is exponentially bigger than the number of states would be exponential in the size of the property. And here, model checking is linear in the size of the formula. Okay? So far only advantages, but you see that there would be also disadvantages. So how does this logic work? In this logic, we have similar operators. So we had before operators always, eventually, and until. Right? We have here the same operators, always, eventually, and until. Only that, you have to remember that always is G. Why? I don't know. Some people say that this comes from many, remember there were two groups that developed model checking, and then some people say that G comes from some French, from the French group and doing something in French. I don't know. I could ask, I know this guy. But in order to remember that, instead of saying always, to remember that G means always, it's the same as box, then I would call it globally. Okay? To remember, let's call it globally. I think it's a silly name, but at least you can remember. And here, eventually, it would be called F. And if you want to remember that, call it future. Globally and F. Until would remain until, okay? So always, eventually, until becomes GF until, or GFU, okay? That's the way you write things. Some people actually put the box instead of always. Now there's another thing, because here also you have to talk about which path you're interested in, okay? So here, you also have to say, you want to say that there exists a path, so exists would be E, or for every path, A. Okay? And these have to come in pairs. So what happened is that you have what we call a state quantifier. It said in a state, I'm going to quantify either that there exists a path or all the paths from that state. So in that state, there exists a path or all the paths. And in a path, we quantify either that it's all the states or there exists a state, and that's an F. Okay, so we quantify for a state, we say well, there exists a path for all its path, and on a path we say for all the states or exist a state. So it's kind of funny, you know, maybe at the beginning it's hard to get used to that, but what it means is that on a state we look at the paths, and from a path we look at the states. And then it moves us back and forth between paths and states and paths and states. So it has to alternate between paths and states. Okay? Which is actually a disadvantage. So there was a way to kill this thing. So let's try to understand this formula. So this formula interpreted from the head of the tree, the root of the tree, it means there exists a path for which in every state P. And this is such a path. There exists a path, the yellow path, in which all the states satisfy P. Okay? It's like there exists a path in which box P. And this thing says here, on that state, if I interpret it from here, it says for all the paths, eventually P. So let's see, I have, how many paths do I have? I have 4 paths, right? So let's see, for that path, eventually P, yeah, because P happens here. For that path, eventually P, yes. For that path, P happens here, and for that path, P happens here. Okay? So the semantics, if you know the semantics for LTL, nothing much new, except for I have these quantifiers that tells you exist or for all, and they are interpreted from a state over the path, starting at that state. And, of course, you have the until. So now you have to write it like that. So it's exist until there exists a path in which P until U. So that's that path, right? P until U. It's along the path, it's the same semantics as in LTL, but it says there exists such a path. And here it says for all the path P until U, so P until Q, P until Q, P until Q, P until Q, and P until Q. Okay? So we know the semantics. Of course, we have negation and the only thing to notice, which is important, these things alternate. So you could say exist until, or for all until, or exist G, or for all G, okay? But inside of an exist, or for all, you can put only a formula of the type G, F, or U, right? Globally, future, or until. You cannot put as a subformula that starts with an E something that includes an N. Okay? You cannot say, see, you cannot say E, GP, or FP. You can say EGP or EFP, but you cannot say EGP or FP. Okay? I have to come in pairs. State quantifier and path quantifier. Okay? You cannot say you cannot say EGFP. You're not allowed to do that. Or EFGP. You know, you would have liked to do that maybe, because EFGP would mean that there exists a path on which for some time forever P. Right? Or GFP means there exists a path on which P happens infinitely many times. But you cannot do that. That logic does not allow it. There's an extension to that logic which is called CTL star, which does allow exactly that. And that's a logic which includes both LTL and CTL. Okay, but that would be more complicated, so let's stick now to this. So there is a solution, and it's always a trade-off. You can solve that, it costs you more. Right? But let's stick to this. Now, you could say things like mutual exclusion is AG. For every state, I'm not at the critical section of both processes at the same time, or always eventually request. There is a path where there is a request. It doesn't require that all the paths will include a request, but there exists a request. Okay. Now, how do we do model checking? And that's actually one of the two groups that invented model checking, and both of them won the Turing Award a few years ago. Clark and Emerson Sista was later a student of Clark. And how do you do model checking? The nice thing about that logic is the following. It's a nice property which does not hold for linear temporal logic. So the nice thing to observe about that logic is that we can do, and this is based on the restriction that I have to write these quantifiers, the state quantifier and the path quantifier in pairs, in adjacent pairs. Because of that, what I can do, it's a really nice algorithm. I can start to do the model checking by looking at the graph, and I would annotate every node with the subformulas that holds in that node. Okay? So I'll start with the propositions, and I go in every node, and if I have a proposition P, I will just mark all the states where P holds. I don't have to take care of negation, because those states which I didn't mark P, they satisfy not P, right? And I do that for all the propositions. And I do that bottom up. So I start with the smaller subformulas, and now I'm going to mark the formula itself, right? So I'm doing bigger and bigger formulas, right? Like if I know that I should satisfy P and Q, I mark P on all the nodes that P holds, and Q on all the nodes that P holds, that Q holds, right? And then I go and look at every node, in which node is already marked by P and by Q, and I mark P and Q. And I go from inside the formula out, and I do that, right? I do that recursively, and eventually all the states would be marked by all the subformulas, including the entire formula, that hold them. This is, I think, a very nice algorithm, right? This is much simpler than the algorithm that we studied for LTL. In LTL, this did not work like that because I had actually several path quantifiers allowed together, and I didn't kind of alternate between a path and a state quantifier. Then I had to translate into automaton because things were dependent a lot on the past, not only the current state, but a lot of the past, and there were different things about the future. So I had to do that by translating into automaton. And also it was a non-deterministic automaton because maybe it depends on several things that happen very late on the future. Kind of, that's more or less the intuition. But here it's very simple. You annotate every state with the subformulas that hold it, and you start by the very simple thing by annotating all the states where P holds and Q holds, and then I'll show you how to annotate the rest. Okay? So it's very nice. Okay? It's a very nice algorithm. And I think also it's not that surprising that they started to work with this logic because, you know, both the algorithm is simple and the complexity is linear in the size of the property, right? So otherwise it wouldn't catch, right? So you want simple things that people would like to use. But let's see, you know, I told you that you annotate all the propositions, and maybe now you can go and do the Boolean combination of the propositions. It's easy to do. But let's do the rest. So what I'm saying is that the model checking algorithm would work on the graph, okay? And let me denote the states, for example, that satisfy property or proposition G by S of G. Okay, that would be a subset of all the states. Those are going to be the states satisfying G, and the complexity would be linear in the size of the state space and the size of the property. I'm kind of cheating here because there are actually algorithms which say, okay, I actually don't want to generate the full state space, so I can do that, and I could be even more efficient. It could be, this is a very advanced comment. It could be actually logarithmic in the size of them, but then it would be exponential in the size of f, or vice versa. So don't worry. I mean, we're looking at this where someone first generated the state space and then did the model checking, and that's the complexity. Another thing is, we'll see later that we can have a data structure which is called BDD, and without data structure we really don't have to generate first the entire state space. We're going to directly do things where the complexity would not be better in the worst case, but in many cases it would be much more compact, and that allowed you in many times to do verification of system with I don't know, I mean, the papers say like 10 to the size of 10,000 states, okay? Obviously you cannot do that with the approach I showed yesterday, right? So with that you may be able to do. You know, the complexity would say no, there are cases where that would not work. So sometimes it works, sometimes it doesn't. So here's the algorithm for doing EFG, and let's go slowly here. So I assume that G is a proposition or itself is a property, and you have already marked all the states that satisfy G. Okay? I told you, you do it bottom up, you start with the subformulas, right? So let's assume that someone marked all the states that satisfy G. We call that state, as in the slide before, S of G. Okay? I did that recursively. Now every state that satisfies G is marked with G, is in the set S of G, and every state that does not satisfy G, so it satisfies not G, okay, is there. This is a property that would not work with linear temporal logic, right? Because linear temporal logic, you want to look at all the sequences, right? So if you say, I have a state, it could be that some of the sequences to that state would satisfy a property and some would not, right? We saw that in the spring example, right? So that's why temporal logic intuitively, linear temporal logic is more complicated. But here, a property either holds in a state or does not. It depends on the state. and it's surrounding, it's future. So what I do is I have this procedure, and the procedure takes all the states that are marked with G, okay, those that satisfy G, and what it does is the following. It has two sets, okay, it starts with two sets. The first set is empty, the second set is initially set to those satisfying G. Okay? Now, intuitively, what would happen is the following. I have two sets, and one would be the new set of states that I mark, and one would be the old set of states. So the only reason I have these two sets is that I keep the old set and the new state. I'm going to progress. It's going to be monotone in the sense that each time, in this case, I have more and more and more states. Right? And how do I know that I finish? Because there are finitely many states. When the old state and the old set of states and the new set of states are the same, I would not continue this loop, so I finish. So I reach what is called a fixed point, right? So it's kind of a function that, given the fact that I calculate the previous iteration, calculates the next iteration, and when the next iteration is equal to the current iteration, it's a fixed point. It means that I cannot continue, right? And because it's a finite number of states, and because the operation is monotone, then I'm sure there would be a fixed point, right? I'm sure that this would terminate. And what do I do in every iteration? So in every iteration, first of all, I check that I need the iteration. So yeah, I mean my old set of states is not the same as the new one, okay? So I take the new one and I keep it in old. So, and now I'll calculate the new one, okay? I'm going to, now, what do I do intuitively? Okay, suppose that I have states which are in this queue. The states in Q, at any point in the calculation, they satisfy the property that from that state there is a path of length, say at any iteration n, there's a path of length n from that point to a state satisfying G. Okay? Because I know that there's a path of size n or less. So if I go now to the iteration n plus 1, what do I need to do? I need now to connect I need now to connect the new states that they have an edge to a node that was in the previous iteration. Let's see it as a graph. Okay? So initially, let's say someone marked all the states that satisfy G. Okay? So initially, there would be an approximation of that property. Would be all the states. It says, this formula says a path satisfied if there's a path, right? If there's a path in which eventually G, or if there's a path into a state satisfying G. So initially, I'll mark just the state satisfying G, right? Obviously, there's a path of length 0 from a state satisfying G to a state satisfying G, right? Now, what do I need to add? This is the 0th iteration. In the next iteration, I'll add all the states that have edges to states that already were in the set, right? So, let's see. Would I add that? What do you think? Does it have an edge into a node that is already in the path? No? Yes? Yes, right? Okay, because there's an edge. Do I add that? Yes. Do I add that? No. That one? No. This one? Yes. This one? No. So now my set of states satisfying an approximation of EFG, actually it's like I have a path of length 0, and in the next state I have a path of length 1. 1 or 0. 1 or less. Now what do I do? Am I done? I make the next iteration. What do I do now? Now I am adding all the nodes that have an edge into a node that was in the state before. Right? So, okay, let's see. Do I add that node? Do I add that node? Does it have an edge into a node that was marked as in the set before? No. This one? Come on. No. This one? Yes. So I'll add it. So that was the second iteration, let's say, if iteration 0 was the first. And now I added that. Now what happens now? Now I'm trying again to add nodes. So I can only add one of these. Do I add that one? No, right? Because there's no edge from that to any of the nodes. And that one? No. So now when I did that iteration, this is the third iteration. The third iteration is equal to the second iteration. What does it mean? That I reach a fixed point. A fixed point of a function that takes a set and calculates a bigger set according to the laws I explained before. Okay? So I reach a fixed point, and indeed, this is exactly the set of states, each one of them satisfying E, F, G. Now, how do I know that the program, if this is the graph of the program, that the program satisfies E, F, G? Because I look at the initial states, and if the initial states are marked, then I know that the program satisfies E, F, G, right? But I do that through marking all the nodes. Let's go back. Let's go back to the algorithm. Let's go back to the algorithm. As I said, there are two sets, right? So initially, Q is all the states, and Q prime is S of G. Now I'm checking that. Sorry, that's not the one. Yeah. So initially Q is nothing, and Q prime is S of G. And at each iteration, I just copy the new ones to the old one, calculate new ones by adding all the nodes such that there exists a state, right, from which there is a transition, and it's a transition to a state satisfying that it was in the state in the previous iteration. Okay? Now this is a notation that tells you there's a relationship between S and S prime such that S prime is the successor of S. But this is a notation I'm going to use now. Instead of saying a transition, I'm going to write a relation which say S prime is obtained by applying an atomic transition to S. It's going to be useful for me, instead of saying transition, to write a relationship. But transition is kind of more precise in the sense that a relationship could be non-deterministic, and a transition usually is deterministic, but it doesn't matter. I can encode each transition as a relationship. Right? It's a relationship between the variables before and the new variables after the transition. Okay? And it will have some condition that would kind of force it to have the enabling condition. I mean, we'll get that. So, if that's what we did. We had 3 iterations. The third iteration, the condition for repeating did not hold because we reached a fixed point, and we terminated and we reported that set as well. Okay, is this clear? So this algorithm, it's I think simpler than the LTL algorithm, right? And it's more efficient in some sense. So let's see another property, EG of G. Okay. So what do we do in EG of G? Let's look again at the example. Okay. So EG of G. What I'll do now is I'm going to start with all the states that satisfy G. Okay. Here I'm going to work in a different direction. I'm going to start with all the states that satisfy G, okay? And that's going to be my first approximation, okay? Now, what I need is I need to find, right? I need to annotate these nodes where there exists a path which is infinite and satisfy G. So my approximation would be, now I'm going to remove nodes that cannot extend the path to satisfy EG of G, right? So let's see. This node has a successor. I would remove every node that is marked but does not have a successor satisfied that is already marked. So this node doesn't have a successor, so I'm going to remove it. Okay? So before I expanded the number of nodes, here I'm going to shrink. Okay? So that node, would I remove it? No, because it has a successor. That node, no. That node, no, right? Because it is a successor of itself. And that node, I cannot hear. I'm going to just stop. Someone has to say yes or no. Can someone say yes or no? Yes. Okay. Thank you. So that one we can remove, right? That one can be removed, and because we cannot extend the path to an infinite one, we cannot extend it even with one state, right? So again, kind of iteratively, we do the kind of extension step by step, right? So we just remove those that cannot be extended by at least one edge, and we repeat. So I remove that, and now what? If we reach a fixed point, I mean, if I do the iteration as before, do I get the same number of nodes? I finished? No. What can I remove? Can I remove this guy? No, I cannot remove it because it's not in the set. This one. What about this one? This one now I can remove because it does not have a successor in the set. So definitely I cannot extend that node into an infinite sequence satisfying G because it doesn't have a single successor, right? I remove that. So now I remove kind of its predecessor as well. And now, did I reach a fixed point? Yes. Okay? So the algorithm is the following. I start again with two sets. Before that, I increase things. So in order to start with two different sets, I started with the empty set and the set satisfying G. And now in order to get two different states, I would start with the full set, with all the states and the state satisfying G. So that would allow me to repeat. So before I kind of extended, and here now I'm shrinking. So initially, unless all the states satisfying G, and then I'm really done, then this is the full set of states. This is the set satisfying G. I'm checking, yeah, it's not a fixed point. I'm copying the new to the old, and I calculate new by taking the old nodes, right? And keeping only, so I take the intersection, those that are old, but also they have a node which is these are nodes which have a successor that is in that set. If it has a successor that is in that set, I keep it. If it doesn't, maybe it was in that set, but it doesn't have a successor that is also in that set, it wouldn't have an infinite path, so I remove it. Okay? So there's two ways of doing things, either by extending the set or by enlarging the set, and this really depends on the property, right? So if it's a property with a G, then it's going to be shrinking. And if it's a property with an F, it's going to be extended. U would be extended, and if you want this R operator borrowed from FTL, it would be shrinking. Okay? So it would be some people call it least fixed point, the stronger, and greatest fixed point, but we're not going to get into that. That has to do with topology, and it's not. So more or less you understand the algorithm, right? So if you want to test that you know the algorithm, then sit at home and try to see what is the algorithm for Ampere. That's a good test to see if you understand the algorithm. So this is the LTL algorithm. Okay? And the two communities, the linear temporal logic community and the branching temporal community, they discussed about what to do for many years. Now, there are some advantages to linear temporal properties. For example, there are properties, and I'm not going to go into that, that cannot be expressed with CTL. For example, I cannot say in CTL a property that needs two adjacent path operators. Like I cannot say always eventually. So I cannot say that if a transition is always eventually enabled, then it's always eventually executed. In fact, I cannot express fairness in CTL. On the other hand, in LTL, I cannot say things about branches. So if I want to say that there's something which is called like a home state, I want my system to always leave the opportunity to go back to a particular state, right? So I have an ATM card, I go to the bank, but I need the property is not that at any point it returns my card, because maybe, okay, I'm just going to keep the card inside and I'm going to, I want to keep it inside. I'm never going to demand it. But there's always the opportunity, that's a home state. I can always go to the beginning where my card is back, there's no card inside, everything stuck. That's a home state. The ability to have choices and to have opportunity is a property that is not expressible in ATL. So they have different expressive power. And for that, there's, as I said, the logic CTL star. Unfortunately, the CTL star logic has high complexity, has similar complexity to LTL. So I'm not going to benefit from all these nice things. A nice algorithm, the low complexity, and the ability to use what I'm going to show now, binary decision variables. Okay, so, and there have been a lot of discussions, a lot of papers. Some of them sounded like militant, like why is CTL good or something like that, or LTL strike back, or CTL stars, all kinds of slogans of people that thought that they were inventing the wheel. Nowadays, I would say, I think that for hardware, people use CTL because of the complexity, because it is sufficient usually to write property to CTL, and because with hardware there's so many states. With hardware you really want to check things very efficiently. With software, we even have more states, but a lot of time you can do an abstraction. There's all kinds of. Let's not get into that. There's a war of which one is better for what and which one is more efficient. But in 1990, a group that included Ed Clark, who's the guy who was one of the inventors of model checking, and a bunch of his students, in particular Ken McMillan, and these were the three others were students, but in particular that was a PhD of Ken McMillan, came up with a very nice idea of how to do model checking in a very efficient way. And what they said is the following. And look, the algorithm we presented here is a very nice algorithm, because instead of translating things to automata, it kind of does things on sets of states. And why representing sets of states explicitly, right? So why keeping a list of states or graphs of states, okay? Instead of that, let's represent states in an efficient way, in a compact way. And the way they represent is what is called BDD, or a binary decision diagram. And the idea of a binary decision diagram is that you encode every state as a string of bits. Right? There's a Boolean combination of some fixed size. Okay? And now you can represent sets of states as a Boolean function, right? So the Boolean function would be true. So suppose that in order to represent a state, I need 20 bits, right? B0, B1 until B19. Okay? So I have a function, and if I set the values, I said B0 is 0, and B1 is 0, and B2 is 1, etc., etc. And the function, it's a Boolean function, say 1, it means that that combination represents a state in the state. And if it says 0, that combination represents a state not in the state. Okay? So a Boolean function represents sets of states, and it returns 1 for every state that is in the state, and 0 for every other state. Okay? That's the idea. The main idea. We're going to see that. And their idea was that instead of calculating things state by state, they showed, or Macmillan showed, that you can calculate the algorithm I showed that have to kind of calculate sets of states all at the same time. So if I want to look at all the states satisfying G, that would be a BDD, a binary representation. But if I want to check all the states that have an edge or a transition into a state satisfying G, all of that would be calculated at the same time, not state by state. It would be calculated over the BDD representation. So it would calculate things on a lot of states at the same time, and it would keep it as a binary tree. Moreover, a lot of times the binary tree would be very compact. And that allows you many times to have an algorithm which is much more efficient. Okay? And that, at least in 1990, was kind of a great boost to null checking, because before that, here is something we formed the paper and say, we could check a system with up to 1,000 states. Now that's not true, right? We can check systems with up to a few million states. But they had papers with kind of extraordinary number, 10 to the power 10,000 states, etc. And they can do that in many cases. So a binary decision diagram, it's a representation that was invented by Randy Bryant, also from CMU. All the people that wrote that paper before are from CMU, and he was also from CMU. It's a data structure for representing Boolean functions. And what is nice about it is it's not necessarily more compact than a full binary tree, but in many cases it is very, very small. Okay? It has a canonical representation, so if I want to represent a set of states, there's always a unique representation. Well, I have to keep a fixed order of the variables, but then there's a unique representation. And I can apply Boolean operations on a BDD, and that can be done in polynomial time in the size of the BDD. So in a polynomial time, I take a set of states and I calculate something about, say, the successors or the predecessors, usually predecessors. In polynomial time, this representation of all the states, I kind of calculated things about all the states, not state by state. Okay? So I do things like, I'm not working state by state, I'm kind of doing things in big chunks. And that's the advantage. And now I'll take it away. It's just a model. So in order to define the model, it's kind of mathematically nice to define it. You don't need the algorithm. The same way as you want to control the sequence, the same way you do not want to work with the visual development. Just in the definition, point of the graph, which is what is called I would say there is a path in which every state in the past will be some state of time. That you can see in that way. In case which is something not allowed, it should allow that So someone asked me a question. I think it was interesting, so let me just answer that to all of you. And the question was that when I define the logic, I said the logic is called computational computation, tree logic. I define it over infinite trees, right? When I apply the algorithm was applied to a graph with cycles, a finite graph. Okay? It's important to say, when I define the logic, the semantics of the logic is defined over a tree. Because it's mathematically nice to define over infinite tree. There's no cycle here. But the tree is the unfolding of a graph. So if I take that graph, then actually there are going to be now two trees, because there are two initial states. So maybe I'm going to connect this to the initial node. Then we have two successors. So that node will have a successor, that one will have two successors. And I keep unfolding it, right? So that successor is a successor of this guy and of that guy, and I will put them in a tree separately. I'm not going to combine them. I'm just going to unfold them. We go deeper and deeper and deeper, and if I see the same state, I'm just going to repeat it. I'm going to get a tree. And that's the way I define the semantics of the logic. Why? Because mathematically it is nice to define the semantics based on the tree. But when I apply the algorithm, I apply it to the graph that generates the tree. Right? I obviously don't do the unfolding. In the same way, I define the semantics of linear topology over sequences, right? The sequence is infinite, but the sequence appeared in the graph, right? And the thing I did in the graph were finite, right? Was actually the path had loops, etc., right? So the path, the infinite path, was just a mathematical thing that came from the graph. In the same way here, the unfolding is just a tree, which is an unfolding of that, okay? When I apply the algorithm, I can apply it directly to the graph. Obviously, I'm not going to generate the infinite tree. The same way, let's say, in a Bushy automata, I'm not going to run the Bushy automata over infinite work, right? I mean, what I do is I build the Bushy automaton. It could accept or reject an infinite word, right? But what's important that the Bushy automaton is a finite graph, and I can use it in a finite algorithm to do logic. Okay? So this distinction should be clear. Okay, should be confusing. I use infinite mathematical objects because of their, I don't know, mathematical niceness or beauty, or because it's easier or cleaner to define it. But in fact, I only deal with finite graphs. The paths, maybe they are infinite, but they are there. I'm not going to wait infinitely long to do anything. So once you understand that, let's go back to the BDD. Okay? So as I said, the BDD would represent set of states, and the way we do that is that we'll have some Boolean variables. So we would represent a state not just by the variables. It would be integer, that would be called V1 and K13 and WM5. I'll represent them and code it as bit strings. Okay? So I have one bit string that kind of encodes the entire state. If there's many variables, I'm going to have like the first 32 bits for the first variable and then another 32 bits for the second. I'm going to call them between V1 and Vn, right? So everything now is a bit string, and if you want to decode it back into variables which are integer or whatever, then you do that. But I only look at the state as a sequence, a finite sequence of bits of fixed length. Okay? So state is a finite sequence of bits. Okay? And a BDD, okay, would be a set of states, but it would be representing a function over these variables, V1 to Vn. Okay? Another thing which I actually already used in the algorithm before is that instead of using transition relation, it would help me to have a So instead of having a transition function, I have a transition relation, and that would relate the current state with a possible successor state under executing an atomic action, an atomic transition. Okay? The notation R S prime would mean that S prime is a successor of S. If I picked up some transition that was enabled at S, I calculated the transformation and I got S prime. And in order to represent that, it's easy to write that as a Boolean function, right? If you look at, I don't know, if A is bigger than 3, where A is an integer with, I don't know, 16 bits, then A equals A plus 1. Okay? I can represent it as a Boolean function, right? It would be represented as using two sequences of bits, the bits corresponding to the current state and the bits corresponding to the new state. Okay? It's easy to do that, right? I have to write, it could be not that nice to see on a paper, right? I have to encode the fact that these bits represent a number which is bigger than 3 or 5. I don't know what to say. And these bits represent a number in binary which is a successor of the representation in that bit. Okay? You know how to represent things in binary, right? The first thing in computer science. Right? That's some sequence of bits represent the binary successor of that sequence. So I can represent that as a relation. And that's going to help me, right? So because everything now I want to represent the sequences of it. I'm going to encode everything with bits. So in order to represent successors, I'll kind of double the number of bits, and half of them will represent the old states, and half of them with prime will represent the new state. Okay? That's an important observation, and now I can work with relations. So relations, I'm going just to represent transitions, but it's easier this way with bits. Okay? If I wanted to use transition directly, I don't know how to do that. And so, what's a BDD? So a BDD is kind of a Boolean tree. Okay? It's a Boolean tree. It represents a Boolean formula. The leaves of the Boolean tree would have zeros and 1. And every leaf, every internal node, this has been like that for 20 years. Every internal node represents a node. Every internal node represents a Boolean variable. Okay? So what happens is I'm going to start at the root, which would be a node representing a Boolean variable. And then I have a sequence of bits, right? The values of V1, V2, V3, etc. So when I reach Vi, I'm at node Vi. If the value of Vi is 0, I'm going to go left in the tree. If the value is 1, I'm going to go right. 0 I would write as red, and 1 as blue. Okay? So here's an example of BDD. Now, when I reach a leaf, it will be 0, 1. And that would mean that if I take the Boolean combination, say 0, 1, 0, 1, depending on the order of the variables and the value I would reach 0, 1, you can tell me if that combination represents a state which is in the set, if it's 1. If it's 0, it's a state not in the set. So it's something like that, okay? So this is the Boolean function, and I'm going to represent it like that. If A, say, is 1, I go here. If C is 0, I go here. If B is 0, I go here, and it's 1. It means that A equals 1, C equals 0, and B equals 0 does not satisfy that. It's not in the set of values of A, B, and C that satisfy that function. Okay? So that function corresponds to states. This is states with 3 bits. Okay? And it returns 1 if that Boolean combination is in the set, and 0 if it's not. Okay? So it corresponds to a set of values. I mean, how many values you can have with 3 bits? 8 values, right? Some of these values are in the set because according to the values of the variables you get to 1, and some are not because you get to 0. That's a binary tree, right? It's not nothing special and nothing sophisticated. Only that it's not going to help you a lot if the variables are not ordered. So let me order the variables. It would be helpful if I order the variables. So let me assume a fixed order of variables. Say A comes before B before C. Okay? So now I write exactly the same Boolean function as before, representing the same set of states, each one with 3 bits, as before, but just written with order binary. And so this is called ODD, the ordered binary decision diagram, and usually you forget about the O. So when you say a BDD, you mean ordered binary decision diagram, otherwise it's not very interesting. Now, what you can do is you can reduce that graph. The entire strength of this representation is that if I have n values, right? If I have n values, the number of leaves could be n. Okay? And the number of internal nodes, okay, it actually would be n plus n minus 1. Okay, so it's going to be linear. It could be not more than internal node not more than 2n, right? But if I need n values, right? N, the number of values is exponential in the number of bits, right? So it's not going to be very efficient. So in order to be efficient, what I'm going to do is I want to compact that tree. And the way I compact the tree is, the first thing is I look at each node, and if its left-hand side and the right-hand side of that node are the same, then I don't need that node. I can go directly from its father to its sons. That's one thing. Okay? So if it has, if I go left and I go right and I have the same subtree below, I don't need to hold it twice. Right? I can hold only one of them. I don't need actually that node. I would kind of shortcut directly to one representation of his children, and the other child looks the same. They're twins, so I don't need to. Okay. And also, if I have two nodes anywhere that they are the same, okay, the subtrees are the same, then I would combine them to one. I'm not going to keep both copies. Okay? So the idea is that if I have any isomorphic subtrees, I'm going to keep only one representative. And I do that bottom up, and I'm not going to prove it, but that gives me a unique representation. There's only one such compact tree. So let's see what happens here. So this is the tree, it's not compact. Okay? It doesn't give me any advantage to represent things like that. And what I did here, I go bottom up, and I notice that I can combine all the zeros, and I can combine all the ones, right? They are all the ones are isomorphic to each other, all the zeros. I don't need to keep all. So let me do that. Okay? And now I go up again, and let's see what happens. Okay? What I'm looking for now is I'm looking for nodes that have exactly the same subtree or same successor. Do I have such nodes here? I'm not sure. I don't think so. Right? I don't think so. So that's not very helpful. But also, as I told you before, if I have a node that when I go left and I go to the right, I get to the same place, then I can shortcut that node. Right? So I can go from B directly to 0. Doesn't matter what the value is. And here, if I have C, I go left or right, I get to the same place. I don't need C. I can go from B directly to 0. Okay? So I'm going to do the shortcut. Fine? I cannot reduce any further. That would be the reduced tree. Okay? So I keep doing that as much as I can. Let's see another example. In this case, it's a Boolean function, and it says that the parity of the 3 bits is even, right? So if 2 of the bits are 1, then it gives you 1, and if two of the bits or 0 bits are 1, it gives you 1, and if 1 or 3 bits are 1, then it gives you 0. 0, 0, 0, the sum of bits is 0, it's 1. The sum of bits is 1, 1, 1. The sum is odd, it's 3, then it's 0. Okay? So that's the Boolean function. And now what I can do, first thing is I can compact the leaves. Okay? Now I go up. What can I do? In that case, not as in before, if I go left or right from every node, I get to different places, so I cannot shortcut nodes. But let's see, maybe I have nodes which look exactly the same. Do you see such nodes that look exactly the same as others? You can see that because you nod and... Let's see, this guy, the same as that. This is so quiet here. No, it's not the same, right? And this guy maybe is the same as that. Yeah. And this guy and that guy, they're the same, right? This has a successor, a left successor which is 0, and right successor which is 1, and the same here. So I'm going to combine these two, and I'm going to combine these two, right? I don't need to I combine them. Combine them. Okay? Can I do something now? I don't think so. That's the okay. So this is the way I combine things. Just to give you a picture, it's not always possible to have a huge compaction. Okay? Not always. Not always it compacts completely or compacts into something that is interesting or very compacted. But let's look at some trivial cases. Suppose I have 25 bits, okay? And I have the empty set. What is the size of the BDD? Size of the BDD is one node. It's the node 0. It has one leaf. That's it. Because it's independent on any of the bits. If I have the full set, I have any combination is in the set. It's also a BDD of size 1. Has the bit 1. It has one leaf, 1. Okay? So the fact that I have more elements in the set or less elements in the set is not necessarily affecting the size of the BDD. It's how many similarities I have. Okay? So it's sometimes hard to get the intuition about that, or even impossible. So sometimes we don't know what to do. Another thing is that if we don't get a good compaction, the good heuristics is to take the order of the nodes and to reorder them. Maybe with reordering you get a better compaction. This is something that tools that use BDDs often. So here's an algorithm that I call restrict. What it does is say f is a BDD function. It's a Boolean function, but it's represented as BDD. And I want to calculate f where some variable x is restricted to 0 or is restricted to 1. It's f, but I assign x, which is one of the variables, to 0, or I assign x to 1. Okay? So what happened is that if I want to assign 0 to x, okay, that means that x would behave, x is a variable somewhere in the tree, it would behave as going to the left, right? Because x is 0. I mean, originally x could be 0, 1, but f, where x is restricted to 0, would behave only according to the left direction of x, right? Because the restriction of the function where x is fixed as 0. So what I'm going to do is I'm going to replace the node x, right? So I take the father of x, and I'm going to shortcut x. The father of x, the node before that, it would go to the left branch of x, the 0 branch of x. Okay, that's how I do it. And if x is set to 1, then I'm going to go to the right branch of x. The father of x, I don't need x anymore. The father of each x in the graph, x could appear many times because it can appear in some kind of level in the tree. So before x I have, I don't know, w. W would go to the right-hand branch of x. That would give me the same function as f, where x is set to 1. Okay? And every operation, what I need to do, I need to compact. What I did before, I applied this algorithm bottom up, and I'm going to compact things. Okay? That's very important. So it could be that now I have a graph with redundancies. I don't want redundancy. Without a proof, again, I tell you that the compaction would always be unique. There's always one compact way of representing things. So compaction would be called here reduce. So this is called the restrict operation, and reduce is the compaction. And these are two typical operations. So here is something that some people do sometimes. They allow to add, and it would be useful to add to our Boolean function something which is like existx or for all x. Okay? Quantification. Now, for Boolean function, if you say existx or for all x, it doesn't add any expressive power, right? Because when I say existx phi, that means either phi where x is 0 or phi where x is 1. And if I say for all x phi, that means phi where x is 0 and phi where x is 1. There are two options because there's exist or for all, they all are Booleans. There's only two options. So the only thing is that when I allow existence for all, maybe I compacted the formula. And if you like complexity theory, if I have a logic with quantification, with Boolean quantification, the expressive power is the same, but finding satisfiability turns from NP-complete to P-space complete. But this is only if you really like theory. Okay? I don't care. I just need that. So if I want to calculate that there exists x phi, then I could just, this is equivalent to that formula, and this is what? This is exactly what I did here, right? This is the restrict. So I restrict x to 0 in phi, restrict x to 1 in phi, calculates the OR, I'll show that in the next slide, calculate the OR operation, and that gives me the exist. Okay? Sometimes I want to eliminate variables, so I would need the exist. It would be very useful. So that's another operation, and of course I need to apply the disjunction, what would be the next slide, and I need to reduce or to compact. Each time I compact. So that looks a bit frightening, but this tells you how you apply any Boolean function. So let's assume that hashtag corresponds to any Boolean function, and or implies if and only if, etc. And I want to calculate a Boolean function between two BDDs, f hashtag g. In the previous slide, it would be f or g. How do I calculate that for g? I have a BDD for f, I have a BDD for g, and I want to do f or g. And then we use something which, we have this focus name Shannon expansion. What does it mean, Shannon expansion? It means you do the following. It means you calculate f, where you set x to 0, you restrict x to 0. We saw how to do that, right? And in that case, x, you need not x. So that would be kind of the case where x is 0. Or when x is true, then you restrict x to 1. So according to Shannon expansion, this is a pompous way to saying, well, if you have a Boolean function, right, then you can do things by, if you have a Boolean function, it was written by a table, okay? So you can partition the problem into two sub-problems by looking at the variable x, right? Now order the table such that in the first half of the rows, in the column x there would be 0, and the second half of the row in the column there would be 1, and calculate separately for both of them, and then you get the new table, right? That's what Shannon expansions actually say. It kind of organizes the table for you, but in fact, for BDDs, the way we can read it is the following. It means that if we see a variable, so if in the BDD we are at some point where we see at the top the variable x, okay, if we go to the right, to the left, right, if x is 0, if we go to the left, okay, what we should have is we should have a BDD tree, where we should have a BDD tree. It's not a tree, right? It's actually a graph. It's a cycle-free graph, right? It was a tree and we compacted it. Now it's a cycle-free graph. So it's a BDD where x was 0. So what it means is recursively calculate f and g. Okay, when you set x to 0. So now it's, remember the Boolean function, calculate things where x was 0, calculate things where x was 1. Now you have two sub-problems, right? They are half of the complexity, right? Calculate that recursively according to that formula, and that would be the left node, because that would be the node where x is 0. And calculate the same thing where you set x to 1, and that would be the right node where x is 1. Okay, so that means recursively, go to the left, assign x to 0, and calculate things with the BDD without the x variable, right? You know where x was, the sub-BDD where x was set to 0, the left-hand part of the BDD, the left-hand part of f, and the left-hand part of g, right? And for the right side of the new BDD, you go to the right, so x is 1, and calculate recursively. Set up 1 as x, take the left-hand part of f and the left-hand part of g. And that also you can do by now, these are smaller BDDs, right? These are half of the BDDs as before, so recursively we know how to do that. At the end, when we kind of unfold that recursion, at the end what we get is we have only one x. We get to the last variable. X is the last variable. And then we have bits, right? So that would be 0, 1, and that would be 0 and 1. And then with Boolean values, we know how to do that, right? So we know that, I don't know, like 0 implies 1, right? So when I get to the level that the BDD, it shrinks in half. It's kind of a recursive, says, do it left and right. Each time you have half of the problem, assign 1 or 0, depending if you go right or left. Do it to the subgraph, and when you get to the bits, then that's just the Boolean value. And or implies if and only if, XOR whatever. Okay, this is clear? It just says recursively go in the tree and calculate the function to the left tree and to the right tree, assigning 0 or 1 depending on the size of the tree. That's what it is. It's kind of pompous. It says Shannon expansion, right? But it's the same thing if you calculated a Boolean function and just said, okay, I arranged that according to the first variable, all the zeros I calculate separately, all the ones calculate separately, I have half of the lines, right? One less variable. Then I do that again, half of the lines. Eventually, you have to work with this. It's nothing very complicated here. But you can do that recursively, and this pretty complicated slide, I'm not going to go too much into it, but this complicated slide, what it does is kind of a formal definition that says what I said before. Only that you have to take care of one thing. Because you unified the left and the right directions of a node if they were the same. Remember, you shortcut some of the nodes. And so if the function at some point does not depend on the value of y, right, the father of y will go directly to the successor of y, right? So if y has left and right successor which are the same, I remove y, and the father of y will go directly to the successor. Yeah. Okay? So if I want to apply that very simple definition, and I'm missing some node, what this complicated thing says, it says, well, if you have, x, now you assign x to 0, you do the recursive thing with x equals 0, you do the recursive thing with x equals 1, you connect it, but if you have x here, but here you don't have x, you have y, then connect x with y. Okay, it just says connect to the highest point that you have, because it's independent with x. Okay, that's all it says. This really complicated stuff. So what would happen is that I have these trees. Okay, so it would say, okay, if I want to calculate some function and some Boolean function that takes care of the left BDD and the right BDD, right? So it's a directly cyclic graph. It's a graph without cycle. Then what I'll do, I'll start with, okay, I'll start with the head, which is R1, S1. I marked all the subtrees, okay? And what I'll do is I'm going to set up x to 0, so I'm going to go here, right? And x to 0, and I'm going to go here. I'm going to calculate now recursively the function between, well, I don't have y, right? I have t. So I can calculate this with y and y, so I calculate between y and t. It's independent of y. So I'll go to R2 and S3, so I'll go here, okay? Now, this is a subtree which I got by setting up x to 0 here and setting up x to 0 here. And the result of that, I would connect back as the subtree where x is 0. Right? That's the Shannon expansion, right? You see how it works recursively. So recursively, go to the left by going to the left in both of them and recursively calculate things on the left. But notice that you may jump at some point more than one variable, and it's okay. It's not going to be a problem. And the reason you jump more than one variable because by compaction, this is independent of y. So actually, you can think about that you have a y here, but it goes both left and right down here, okay? So you get that, and if you calculate that, and if you went and carefully calculate that, you see that you have to calculate these subtrees. These are subtrees, and that will give you back that as the BDD. And of course, you need to reduce, you need to compact that, okay? But there's one problem. If you notice, I don't know if you notice, there's one problem. So, okay, I do that, and I'm going to calculate all these things. But if you notice, you see that I have here R6 and S5. This is easy. These are bits, R6 and S5. So if I wanted to calculate the end of these, the end, that would be the bit 1, right? 1 and 1. Now these are the same. Let's see. Let's see. These two are the same too, right? These are the same. Now that's a problem because I worked on that recursively, And now I get here, and I did that again. I wasted no time. Okay? When I reduce, when I'm going to reduce, actually I'm going to combine them, right? The BDD, after doing that, I'm going to combine them. There's no need to do that twice. Okay? So what you do here is that you apply a principle which, again, in a bombastic way is called dynamic programming. So whenever you do this, you go down and you calculate the pairs or the subtree, you put a name to it, and you keep it. You keep in memory a pointer to that subtree, and when you go up again, when you get down to a pair that you already processed, then you don't recalculate, you just combine it, right? Because there's no need. If you didn't do that, this dynamic programming, then one can show that the complexity of doing a Boolean function could be exponential. That's a lot of wasted time. There's no need to do that, right? And without that, it would be linear. Okay? So use dynamic algorithms. Here I kind of colored in the same way all the isomorphic subtrees. So I only need to keep one copy of all the greens, all the purples, all the light blue. Okay? And all the blacks. No, these blacks are not the same. This one separately, this one separately. So this one, and this one. Okay? So we do that, and so that gives us also, we apply reduce, but the dynamic programming also would reduce for us and would prevent us to recalculate this. Good. So now we do what we call symbolic mode checking. So now we're going to take the previous algorithm for CDL and the principle of BDDs, and we're going to combine them such that, remember what we did is we calculated sets, we updated sets. So each one of the sets, remember there was a current set Q and the previous set Q prime, or vice versa. No. Q was the previous set and Q prime was the current one. And now Q and Q prime would be two BDDs representing sets of states. Right? So everything I'll do is I'm just going to do calculations of BDDs. I'm not going to go into separate states. I'm going to calculate things directly as Boolean functions of BDDs. And since these are going to be big Boolean functions, I'm going to apply to them or, etc., and, etc., I'm going to use exactly the BDD operations that are already explained. Okay? We're good? Now, the principle in which this works is very similar to the principle of LTL, because the way it works is that I can think that, say, how do I calculate EF of phi? EF of phi, there exists a path of phi holds, means that either phi holds now or there exists a next state. I forgot to say there exists next state. And next, which was a circle, is x. So I write it as there exists a next state. Either phi holds now immediately, that's fine. Means there's a path that reaches phi if phi holds now, or there exists a successor in which I get into a state where there's a path that's satisfactory. It's very similar to the the equation I had for eventually in linear topology, right? Then I used until because I reduced everything to until. Here, if you took the eventually, it's the same, right? Either psi hold now or phi holds and there exists a successor in which phi until psi. And that notation means that you can calculate that, but kind of unfold it more and more and more and more times. So you repeat, and instead of EF, you repeat putting that thing and again and again and again. So if you do that many, many times, because the graph is finite, basically what you want is a fixed point. You want a set of states. You have a set of states that satisfy that if you apply that equation to that set of state, you get that set of state back. That's why it's called a fixed point. It's a function It's a Boolean function that what you're looking for is the solution that if you take that, the value of z and you apply that function, you get back z. It's not important to understand now, but there are cases where if you have mu, that means the least fixed point, and that corresponds to the case where you can calculate that by starting from the empty set and increasing the size of the set. And greatest fixed point is where you're starting from all the states and you're decreasing. That, remember, I had two algorithms. One was for EF, and that was actually the least fixed point, right? I started from an empty set and something, and I increased monotonically. And there was EG, where I started with all the state and decreased. That would be greatest fixed point. Of course, if one wants to prove that this is the least fixed point, the greatest fixed point, one has to really define all these things, to use lattice theory. It's all beautiful and interesting, but it's not important now. It's just that this is the notation that we use. But in fact, to do that, okay, again, let's note that we have this relation R. So if I have, say, 3 bits representing a state, then I can have a Boolean function that represents that these 3 bits are the successor of these 3 bits. So it's a Boolean function on the number of bits that I need to represent a single state twice. So the unprimed version is the current state, and the prime version is the next state. Okay? So I have a function, and if I have 6 bits that satisfy that function, it means that if I take the first 3 bits, okay, and I apply a transition, I can get the second 3 bits. It means that the later 3 bits, the prime 3 bits, are a successor of these 3 bits. And before that, we have transitions, right? We have many transitions for the atomic actions of the program. And now I don't have to have many transitions. Remember that when I moved from a program to a set of transitions, I put all the transitions in the same basket. I didn't care about the structure of the program or concurrency, etc. It was simplified. Now it's even more simplified because I can write one relation that corresponds to all the transitions. We just say that these 3 bits represent the successor under any transition of these 3 bits. Okay? Either I take the first transition, the second transition, etc. I don't need that. So this is even a simpler representation. Of course, it's also a more complicated. It's a more general representation because before that I have an assignment, and so the successor was a function. The successor bits was a function of these bits, and now it could be that I have several combinations which are successor of the same combination. This is more general. I don't use that generality. It's just it happens, right? If I want non-deterministic transition, then this is also good, but I never use non-deterministic transition. And now what I can do is the following. Okay? Remember that I have this kind of fixed point equation. That I wanted a fixed point, a set of states represented, say, as a VDD, right? Such that if I apply Ex to that set of state, okay, Z, okay, is a set of states, okay? That says in the next state there exists a next state where Z holds, or phi holds, actually now. That's a set of states, and I get a result, which is a set of states. This is a function, it's a Boolean function. You take that and returns, you take the set of state Z, and it returns a function. It gives you a set of states. And I'm looking for a fixed point, remember? I'm looking for the result where I'm going to apply that function and get back the same state. Because that's the solution, right? If you take, an hour ago I showed you an example that takes a set of states and reduce until it gets something that returns the same value, right? That's the fixed point. So this basically is the fixed point, least or greatest, depending if it's for all or exist. I mean, if it's G or F. And that's what I'm looking for, okay? So I can use this fixed point. Again, this comes from this equation. I wrote that formula, this equation. I said that the solution for that formula is a set of states that are the fixed point, the least fixed point of that location. That I take Z, I apply that, and I get back Z. So instead of actually, here it's the smallest set, it's the least fixed point. I didn't prove why it's the least. Or the greatest. It depends really. I mean, you see EF is the least, and EG is the greatest. And we don't care now why. So I'm looking to calculate that, and that's exactly what is in this expression. Okay? So what I need to do here is I need to notice that phi, okay, is something, some expression that tells me something about the current state. Again, everything will be a BDD, so phi would be something that represents some set of values, okay? And this is next time there exists a successor where Z is true. So what I really want to say here, okay, I want to say that there exists some successor where Z holds in the successor, but Z holds in the next state, right? So in order to express this thing, what does it mean for the current state to be such that the next state is in Z, is in the set Z? Okay, it means that I look at the current state, I apply some transition, and then I go to Z, I'm in Z. It means that if I take the relation R, that's the relationship between this state and the next one, I write Z as Z prime, because in the next state Z holds, so Z is on the prime variable, Z is the variable in the next state, okay? That means that I am in a state, so this is a formula, it's a Boolean formula with two n variables, such that the current state is related to the next state, where the next state is in the set Z. This can be written as a Boolean formula or a BDD. So I don't care about the next state, I want just those states now that have a successor. So there exists a next state that is in the set Z. Okay? Remember Z prime because it's in the next state. I have to use the prime. So because of that, I want to eliminate. There exists a next state satisfying Z. So I have to write to eliminate the y variable in the next state. So I write there exists prime one, etc., etc. So I eliminate. There exists a next state satisfying Z. So I need that formula. It looks a bit complicated, but it's not. What I have here, a BDD representing the states, the successor state, the next state that are in the set Z, that satisfy the formula Z. I have a relationship between the current and the next state that is a BDD over two n variables. I eliminate the prime variables because I don't care. I just want them to satisfy Z. But I don't care what they are, so there exists some value. This is a BDD, this is a BDD, this is a BDD. I'm using this apply of a function. This is a BDD. I use the BDD where exist, right? Which I show all of these. I show you all the way up to the. Okay, so this is how I get the next time Z. And now I need phi or, so there's a BDD corresponding to phi, and I say phi or t is that BDD. This is again a BDD, and I use the apply on the or operator. Everything is BDDs, right? So the only trick is, everything is represented as a BDD. A BDD is a set of states. I can use the prime variables to represent the states in the next state. I can use the R relation, which is a relationship between the prime and unprime variables corresponding to atomic transition. I can eliminate the successor states where I don't need their value, I just need them to satisfy something by using an exist. And all of that are the set of BDD operations I just showed you. And each time you apply all these, a lot of stuff is going on here, right? Each one is just BDD. So a BDD model checker is exactly doing that. It's going to apply this. And remember, this is the algorithm as before, remember? Except for here, instead of writing there exists a successor that is related by R such that it is in the set, instead of that, here I replace it with that expression, and that expression is this BDD calculation. So all of that is just a BDD calculation of some stuff. And in every step, I calculate things directly on a set of BDDs, I get a new set of BDDs. So Q and Q prime, instead of two sets of states, there are two BDDs representing each other. And how do I know to stop that I reach a fixed point? I just check that the two BDDs are the same. It helps me that the BDD representation of a set is unique. If I have the same order of variables, I don't need to do any Boolean complicated thing. I can just check the binary trees. You know, I can check them in linear time because they have exactly the same representation if they're the same. So everything I did before, I repeat now, and it's a BDD. And this turns out to be much more kind of efficient, in particular for hardware. And that's what people started to use. People in hardware claim that this is more efficient, that this is good. They say, hey, come on, why would you use any other algorithm? Because once you have to go through, I don't know, 2 million states, I can represent 2 gigabillion states. Maybe it would be compact, maybe it would be a very small BDD. Remember, a BDD that includes all the states with 72 variables has size 1. It has one leaf. On the other hand, BDDs could be large. But people from software, they claim several things. One thing is that logic is not always sufficient. I mean, in software, things are related also to fairness. I cannot even express fairness with this logic. Another thing is that this works very well when you have very short counter examples. In hardware, you have very short counter examples. In software, you really need the very long counter example to show how you reach things. That works well because you're not generating the counter example. You just generating the successor, and then say yes or no. Okay? And if you have a counter example of size 3, you can kind of recover it. People in software say that for software, I really need things like speed. This is like SMV, new SMV. This other system doesn't work like that. What I was teaching yesterday is more like speed. Okay? So this is so here, and here is okay, it's the same for calculating the EG, right? It's the same procedure as before. In fact, the only change is now I use a different function, right? This is a different. Oh, this is an until. Okay, this is an until. So the only difference is that this is an until. And another thing is I have to make sure if I need to calculate the weakest fixed or the least fixed point or the greatest fixed point. But the only difference between least fixed point and greatest fixed point is that with greatest fixed point I start with all the states under use, and with least fixed point I start with no state space. All state space, greatest fixed point, all states are a very simple function true. No state space, no states, empty set of states is false. Right? So everything is simple. It's exactly the same thing. I just feed up that kind of formula. I show how to do that very easy. Okay, so next lecture I'll conclude by showing you something a bit different. Instead of model checking, I'll show you runtime verification, and then we'll wrap with that. So we'll have a break.
Enggak, Pak.
Okay. Okay. That would be a shorter lecture, I think, because if you're all tired, in particular. So I'm going to do something different. These are new slides. If you find errors in these slides, you saw that there are slides which are 20 years old. Most of them are not, but still have bugs. These are slides I did yesterday in the hotel here, so they might have some bugs. I think this is interesting stuff. Both the CDL part and that part is not in the book in Chinese. Okay? CDL part is in the model checking book, and this is not in the model checking book. It's not in either book. But this is new stuff. I'm kind of nowadays more interested in that. We had this discussion in the break about which tools really support model checking, and there's not a lot of tools. I mean, you can use Spin, you can use SSD or USMV. There's not a lot of tools. So companies sometimes have their own tools, like IBM or Intel, but by and large, people are still doing testing, and so what do people do? And this is kind of an emerging field, also in form of methods, which is called random verification. And what is random verification? So sometimes, or a lot of times, it doesn't make any sense to check all the executions. The model checking is comprehensive. You check all the executions, or an abstraction of the executions, so that it's supposed to represent all the executions. And sometimes, because of the state space explosion, it's really impossible, even with BDDs. We know that with BDDs, for example, they compact very well, but if you want to verify hardware multipliers, they do not compact well. Still, it's not going to be exponential in the size of the world. So sometimes what people do is either they take statistical results. It's called statistical model checking. So they do samples, okay? They sample the executions. In some sense like testing, but they use randomness, okay? And the reason to do sampling is twofold. One reason is because of the complexity. And another reason is that sometimes we have an algorithm that would work with some probability, and what we want is the actual statistical result, right? So model checking will give you yes, no, counterexample, but you want to say, oh, that would happen with, I don't know, 30 plus minus 5%, and will give you some kind of a statistical measurements and some information about how reliable is the result. Okay, so this is also something that people use a lot now. Unfortunately, statistical model checking, of course, I mean, it's statistical, so you know that you have to take statistical error. And another problem with statistical model checking is that the whole thing, random verification, would work with finite sequences. Because what we're going to do now is we're not going to use these automata over infinite words. We use them as a mathematical tool to translate from LTL, but we're going to actually follow the executions. Okay? Follow the executions until some time, and we want to make a verdict whether a property holds or not. Okay, and this is runtime verification. And you know, in the general sense, runtime verification is just applying some kind of processing to an execution and obtaining some results. So it could be a verdict, yes or no, but it could be some calculation. Okay, so I'm going to talk about runtime verification, which in particular, what it wants to do is to give you a verdict whether an execution satisfied property, which is a temporal property, or it is a Bush automaton. Remember again, I follow the execution only finite amount of time. So I see finite number of events, and I want to decide whether it's satisfied or not. And of course, if it's finite, maybe I cannot, right? If I want to say eventually always P, meaning P happens infinitely many times, it doesn't matter how long I'm going to check it, I'm not going to be able to say eventually always P. Okay. So what is runtime verification? I want to do monitoring execution. So here time goes from left to right. And I have a sequence of events. Okay, so I see events. And I have this monitor, the runtime verification tool. It has seen a sequence of events. The events that it has seen so far, it has its own internal state. And now a new events come, and now it is going to change its internal state. And it's going to see if it can give a verdict. It would say, already satisfied the property, or not yet satisfied the property, already failed the property. When can it say that the property is already satisfied or it already failed? Okay, since the properties are infinite sequences, okay, if it sees a finite sequence and says the property is satisfied, it means that whatever way I'm going to extend that sequence into an infinite one, it's going to satisfy the property. Okay? If I know that whatever way, it doesn't matter what I see next. The future is not important. According to the prefix I see so far, the property is satisfied. Then I can give a positive value. If I say that, if I see that according to the current prefix, it doesn't depend on the rest of the execution. Anywhere I'm going to extend that sequence, it would fail to satisfy the property. I'm going to give you a negative verdict. Okay? Now it could be that I cannot say anything. It could be that I cannot say anything. It could extend to something that satisfies the property or does not satisfy the property. In that case, I cannot say anything at the moment, and I keep monitoring that. Okay? So suppose we're monitoring the, I don't know, the nuclear reactor at Fukushima, right? And I have the property that says that always the number of events of, the number of continuous events that I saw that the temperature of the reactor is greater than the normal is no more than 3, and also in the last 5 states I didn't see a red light, and that's good. Okay? So I can monitor that, right? But so far, I don't know that the property that this happens all the time would be true or false, right? Because I only see a finite sequence. But I know that so far it is not violated. But at some point, if that property will not hold, okay, then I know that the property is violated. If the number of events that tell me the temperature is bigger than the normal is greater than 3, it's 4, okay? In that case, I give a negative verdict. In that case, there will be an alarm, and I will close the reactor, and people will start to escape, etc. Okay? So in many cases, what I'm looking for is the negative verdict. Okay? A lot of times, the positive verdict is not very interesting, but I achieved something. Basically, a positive verdict would say, I'm not interested anymore to follow that execution. The negative verdict is important because then something really bad is happening. And this also nowadays is used in order to do some kind of program synthesis, or in order to control program. Okay, so I'm going to write, or I'm going to develop a monitor. It's going to follow an execution. And if something is wrong, I take care of things. I would avert some of the situations. Also a way of programming. Okay? Now, when I do runtime verification as opposed to model checking, I'm not keeping the entire state. This is pretty practical, I think. This, to my opinion, is simpler, but it's more practical. So what I'm doing is I'm looking at certain events, and I get these events are kind of chunks of information, and the system that I'm monitoring is sending me events one at a time, a sequence of events. So in order to do that, what I need to do is I need to, what's called to instrument the code of the system. So I need to add some stuff, some procedure to the code that would take the information that is monitored and we're going to provide that information to the monitor. Okay? So I'm not monitoring the entire states. It's not model checking. I'm monitoring a sequence of events, and that these events would contain limited amount of information that is relevant to the property that I want to monitor. And I need to instrument the code, and of course, I assume that instrumenting the code will not change the property. Like if the property that I want to check is something in real time, and the instrumentation will be too slow, then that property would be violated just by doing instrumentation slowing down the system. So what happened, I see the next event, and then I check if I have a verdict, yes or no, and then I change the internal value of parameter verification, monitor, and then I see the next event, etc., 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 and I keep doing that further. Now it's also important that the amount of work that I do is not too large, and that the amount of memory that I use is not too big. So it is important that I'll be able to use finite amount of information. So if I have a sequence which is bigger and bigger and bigger, in fact what happened is that this runtime verification monitor, kind of, its internal state is kind of a summary of the execution. It's a finite amount of information. I hope it's finite, because if it's not limited, it grows and grows and grows, then I will be limited by the size of the sequences that I can handle. So I need that information will be limited. Okay? It would summarize, in a minimalistic way, the execution so far, such that monitoring would depend only on that information. I don't want to remember that information. Okay, so that's important, because there's different algorithms. Runtime verification can be online and offline. If it's offline, it means that the sequence already happened, right? I keep these events. Okay, the instrumentation generated a file with events. I keep these events, and I'm going to run over it. And if it's online, then in fact I have to fasten up, capture the event, and calculate and change the internal structure of the runtime verification and continue. Okay. Also, it's interesting that runtime verification uses different kind of formalisms. Because I was teaching temporal logic, I'm going to show temporal logic and how we use automata. Runtime verification usually looks only at negative verdicts and properties that you can decide at some finite time if they are variable. In many cases, use past temporal logic that only looks at the past, because it only can see the finite part. So it's only dependent on the past. That would be what's called safety properties. I'm not going to go into that, but that makes things simpler and in some cases efficient. Okay, so some constraint. We cannot be comprehensive. So we're not guaranteeing that the code is correct, that the system is correct. The atomic reaction cannot have failure. We're just following one execution, or in statistical model checking, we are providing some kind of a statistical information, and it is limited as statistics. We are saying that there's lies, big lies, and statistics. So statistic is statistic, but you don't need to trust it too much. Okay? Unlike Bushy automata, unlike model checking, which uses Bushy automata, we're only checking one sequence at a time. Right? So not comprehensive, but also we're checking finite sequences. So we need to make a decision when we can over the finite sequences. Another thing, we see one event at a time. Event is the information that the instrumentation gives the monitor. Okay? It's hard to apply random amplification to concurrent system. Because if things happen independently, then you have to make sure that they will be monitored in a consistent way. There are ways to do that with logical clocks and all kinds of things, but then it becomes difficult. So let's see, I think this actually will be very short because I'm not very quick. Let's see what happens. Suppose I want to guarantee that the property I want to satisfy is always P. Okay? Always P, always the temperature in the reactor is not bigger than the normal. Okay? So this is an invariant, this is a property in all the states. And I can write always P. I mean, this would also be a good exercise for what I was teaching about the translation, because I can translate that into this Bushy automaton. Okay, it has one initial state, it is accepting, okay? And if I'm in P, always P, then I'm accepting infinitely many times. But if I have only, even one and only not P, this would be not, then I'm getting here, that's a C. I never get out of that C, and this would be not accepted. Okay? So I may want to monitor that property, and if I do that, okay, what is important is that I should be able to do that as fast as possible. So in fact what would happen is that if P holds for the entire execution, I mean the entire execution is infinite, right? I would never be able to tell you that P holds always, right? Kind of, say, the nuclear reactor stopped working after 100 years, so yeah, it was holding always, but I would never be able to tell you that. So a positive verdict is never given here, but a negative verdict will be given here, and as soon as possible. So once I get to a state in which P is not true, right? You see P, not P. The very first time that P is not true, I'm going to be here. So a negative verdict, which is the one which is important here, that is important here, will be given immediately. Okay? So the point is that not always we can get both positives and negative verdicts. Okay? Sometimes we can get negative verdicts, sometimes we can get positive verdicts, sometimes both, and sometimes no. Okay? But usually, negative verdicts are the ones which are important, because this is a situation which is dangerous, which we want to avoid. So that's a property where only a negative verdict can be given. Let's look at that property. Eventually P. Okay? Eventually P is this automaton. I start here. And once P holds, then I get to that state and I stay here. Doesn't matter what happens. Even once, if P holds, then I'm going to accept, right? Because later I'm going to be here. Okay? So here, it's kind of this less common thing that you want to check using random verification. And now you can get a positive verdict. Okay? So once P held, we say, okay, no need to monitor anymore, it was true. Okay? Unfortunately, if I want to check that eventually P holds, that's not something which is monitorable. So there are properties which are monitorable. Monitorable means that within a finite sequence, if it holds or if it doesn't hold, I have a verdict. It can be positive monitorable, where I have a verdict that the property holds within finite time, or negative. And this one has a positive verdict, but not a negative verdict. So if P does not hold, right, I cannot conclude that eventually P is not true. I just didn't see enough, right? So it's important. That property is less efficient or important or interesting, whatever, for runtime verification. For monitoring, usually we're not interested to know. But maybe yes, maybe what you do is you have some plant and you want to know when the process is done. So you apply monitoring and then you kind of bring the manager is done. Okay? Notice previously I could get negative verdict, which is the common thing that I use runtime verification for, but not a positive one. And now I can get a positive one, but not a negative one. What happens here? So this is a property which says that P holds infinitely many times, right? Always eventually. That corresponds to this automata. If P is true, then I go here. Should have a P here in that edge, and not P here in that edge, sorry. So if P holds infinitely many times, I accept. Doesn't have to be continuous. And if not P holds infinitely many times, if P holds finitely many times, so I'm here only finitely many times, then I do not accept. Now, is it monitorable? Monitorable means that I can figure out in finite time if it's true or not. Let's see. I cannot conclude in finite time that always eventually P, right? I never know if P is going to happen infinitely many times. I only saw finite many events. Okay? And I cannot conclude that from some point on, P would never happen. So eventually always not P, right? The negation is not true. Because I don't know, right? Could be that P never held, but at some point you start to hold infinitely many times. So it is not positive and not negatively monitorable. Okay? So there's this issue of monitorability and non-monitorability, and there are procedures to decide whether something is monitorable or non-monitorable by just looking at the property, you do crunching on that. It's a double exponential procedure, so it's doubly exponential to the size of the property, but it will tell you whether it is monitorable or not. And here's the dual property, eventually always P. It says from some point on, P would be true. Now this automaton, remember, this is a non-deterministic automaton, and there's no deterministic one. And this is not monitorable as well, not positively and not negatively. Right? I do not know that from some point P would hold forever, even though I saw for the last 20 days that P is true, could stop. Right? And I'm not sure that it's not going to happen. Maybe P did happen in the last. I don't know. If I see infinitely many times that P would not happen, right? In the last 20 days, maybe P never happened, right? It doesn't mean that at some point it will not start happening and never stop. So this is not, I cannot get a positive or a negative. So how do I do the monitoring? Okay. So the thing is that there are properties which are monitorable and non-monitorable. Okay. And the most important properties are those which are positively or negatively monitorable. There are properties which are not monitorable at all, like this property. There are complicated properties which in some cases you get a verdict, positive or negative, and in some cases you don't. This is all the combinations, right? So what you can do? Usually you're interested in properties which are negatively monitorable. So usually you go with properties of this type, okay? But you could be interested in positively monitorable. And in both of these cases, you can generate a deterministic automaton that would correspond to the monitor. And here's the way that you do that. Okay? So first of all, what we learned that some temporal properties can be monitorable positively or negatively, or non-monitorable, or any combination of that. After a verdict is given, I mean, it's monitorable because I could decide yes or no without looking further, right? So there's no point to look further if I have made a verdict. Another thing is that I can always, I mean, if something is monitorable, in fact, positively or negatively, in fact, I can always generate a deterministic automaton that would catch that information. So how do I do that? Okay. So the way I do the monitoring is the following. Someone gave me a LTL property. I wrote it as phi here because I didn't have the character phi. Okay, this is a property phi. The negation of the property is not phi. So what I do, as before, I translate phi into a Bushi automaton. Let's call it A of phi. That's a Bushi automaton, possibly non-deterministic. That is the translation of the property. And I translate not phi also into a Bushi automaton that recognizes the language A not phi. These are automata, these are Bushi automata, these are automata with infinite words. Okay? Now what I do, I'm going to simplify these two automata. And it's not interesting for me to look in an automaton at the state from which I cannot have an accepting cycle. Remember, in order to accept, I need to go into an accepting state and then to cycle through it. We proved that if I have acceptance, then there's going to be an ultimately periodic sequence, right? So every state from which an ultimately periodic sequence, or from which I cannot reach a maximum strongly connected component with an accepting state, every such state is not useful. I can erase it, right? So I can kind of minimize this automaton by erasing such non-useful state. From such a state, if I'm there, I'm not going to accept anymore. With that execution, if it's non-deterministic, maybe there would be another run of the same execution, but not this one. It's not useful, right? So let me erase all the states for which I cannot get into an accepting cycle or a strongly connected component with an accepting state. It's easy to do, right? I look at the graph and I do the graph algorithm. I do that for both Bushi automata, and I get these reduced Bushi automata, and they represent the language, an automaton that recognize the language of phi, and the automaton that recognize the language of not phi. Okay? And the problem is that when I have a Bushi automaton, it is possible that the automaton is non-deterministic. If the automaton is non-deterministic, what will happen is that if I'm going to just follow one run of it, at some point I may stop, blocked, and there's no way to continue, but I should have followed another execution. Right? So now what I'm going to do is I'm going to follow the subset construction. The subset construction of finite automata tells you to start with an initial state. Let's assume there's a single initial state. Okay? And then, say, if you saw letter A, look at all the successors of that state under A, and that's the next set of states, right? And now, if you say now B, for example, look at all the successors of these states after a B, and that's the next set of states. So I get an automaton that moves from a set of state to a set of state to a set of state, etc. Okay? That's the subset construction. As I showed you when we talked about Bushi automaton, the subset construction is good for finite automata with finite words, but it's not good for Bushi automata. If it was, that would kind of negate my result that sometimes I don't have a deterministic automaton. But I still do that. So I take the Bushi automaton, and I still am going to do the subset construction, the usual subset construction for finite automata. Now, what would happen? Suppose I take this automaton A of phi, and I do the subset construction. So every state, remember the subset construction is a set of states where I could have been, all the possible states I could have been with the prefix and so forth. It's not deterministic, so it's all the states. It could be that I split and I unify, right? So I could go in that direction, and then for both directions I get to the same state. But these are all the states that could be after C, say A and B. Now, if after some point the successor of some state, now I see a D, and the successor of that state under a D is the empty set, means that there is no successor for any of these states with D, right? What does it mean? It means that I cannot anymore satisfy the property, right? Remember, I erase all the states that are not helping me to satisfy it. So it means that from any of these states, maybe they are successors, or these are not useful successors. These are the successors that would not lead me to an accepting cycle. So if I'm monitoring my sequence with this subset construction automaton, and I get to the empty set for A of phi, subset construction of A of phi, I get to the empty set, it means there's no way to satisfy phi anymore. It means I know now that phi is failure. It's a negative verdict. Huh? Okay? So that's the way I get a negative verdict. I do the same for the negation of this property, right? So I take the automaton for the negation of the property. Remember, that would be the automaton that recognizes all the executions that do not satisfy phi. Right? And that was also the trick in model checking. Instead of taking this construction and complementing it, I negate phi and then I do the translation, right? Translation is, I showed you a translation from LTL to Bushi, right? And I do the same thing. Now at the same time, I monitor my execution according to the subset construction of A phi, but I also monitor my execution according to the subset construction of A not phi. So I'm running them synchronously with two automaton, two deterministic automaton. One whose states are the subsets of states where it could be this automaton, and one with the automaton subsets of that automaton. And now if with this one I get to the empty state, it means that now I'm in a state where there's no way I can satisfy not phi. Which means I know that I can have a positive value. So to know that the property already is terminated a finite amount of time means that in the automaton that satisfies, in the automaton for the negation of the property, subset construction got me into an empty state. There's no way to continue an execution and satisfy the property. And that's a decision procedure that allows you to decide positive or negatively for every property. However, notice that in many cases, if someone gives you a property, the first thing he would do is not to do this construction, but he would apply some algorithm, which is not very complicated. It actually uses that as a procedure, and it calculates whether the property is monitorable. Monitorable in the way you want, whether it could give you negative results or positive results. Sometimes it's kind of half monitorable in the sense that it could still give you a positive results, but it could be that at some point it would not give you any good. So there's all kinds of combinations, but you can decide it in advance in order to check whether it makes even sense to do the monitoring. And after that, if it makes sense, you do that construction and you do the monitoring. So there's all kinds of things to do with runtime verification. As I said, statistical model checking, in particular when there's properties which are related to real-time constraint, okay, it uses runtime verification as a procedure because it randomly is checking different executions. Again, knowing that it looks each time on a finite sequence. So these would be properties where you would look at some finite portion of the execution. You're not going to follow them forever or as long as they survive. You're going to say, okay, I'm going to check them for 20 states. And then in statistical model checking, which is also a very active research area now, you have all kinds of statistical conditions on when to finish the statistical model checking. When you had enough representatives that would give you some kind of a statistical results. I know that at probability such and such, so and so executions, I mean, that percentage of the execution satisfy the property and the rest satisfy the negation of the property. Okay? And that uses heavily all kinds of statistical conditions. I'm not going to do that. Something which I think is interesting. Nowadays, we are also interested in runtime verification with data. So the events may carry data. Now, we talked about model checking. That model checking, there are some cases you can do model check for infinite state spaces. You use all kind of decidable decision procedures. I would say that in many cases it doesn't work. It works for particular domains, and I would say that for most domains it would not work. Model checking over infinite state spaces. But in runtime verification, a lot of time you're interested in events that carry data. The data doesn't have to be bounded. It could be that you get some measurements, say integers, but they're not bounded. Any integer can happen, and I can move from propositional temporal logic into first order temporal logic. I could say something which is parametric. I could say P of X. I could say there exists X or P of X implies that eventually there exists Y or P of Y. So I can move to first order logic, and in many cases this is decidable. It's used, for example, in NASA when they look at the traces that are sent from the Mars rover. I mean, I have a tool on that with a guy in NASA with Klaus Hagelin. And nowadays, many of the RV tools are with data. And because I'm not doing the complete model checking, I'm just following one execution, that happens to be decided. Well, depending on your assumption, but it is. So I think that's very nice. And so this is temporal logic where you can use parameters and you can use for all exists on the data. For all X, exists Y, etc., etc. And I think that's really nice. One uses runtime verification to guard the program. Okay? It's called fencing. To put a fence on the program, kind of synthesizes a controller. I'm going to write the program, ignore that I have problems, but allowing some kind of control points, and I'm going to write an RV monitor that would detect when these problems appear, and then it would kind of avert the problem. That's also very popular. And I think my opinion is that a lot of time simpler is better than more complicated or more sophisticated. And I feel that the world is going more in the direction of runtime verification. And there would be a lot of tools for that. There already are many tools for that, but it's pretty useful. So, first of all, thank you for coming. And many of you stayed until the end, so I'm very happy. Thank you very much. The slides, I keep editing them, and during this week, I also made some changes. So I think if you got some slides at the beginning of the course, it's not the last version. But I'm going to go home and make also some version which is based on I saw that sometimes there are things that I skipped or things that I thought that I could fine tune the lectures. So I'm going to send Professor Bull more kind of a more updated version, and you can get it from him. If you have any questions, you can send me mail by this mail. I know that Gmail is a bit problematic here to receive. Hopefully you can send. Otherwise, also this email, they are copy of each other. This is my university mail, that's my personal mail, and they both are sent to the same place. So if you have any questions, don't hesitate to ask me. I'm happy to explain. Okay? Thanks very much.
Thank you guys for coming, and let's So thank you again, and if we have any questions, then send me emails or email to the